Start recording.
When are we gonna?
When are we gonna have the quiz for this? I would like to do it on Thursday, but apparently everybody's got tests on Thursday.
Yeah.
So I was thinking then Monday maybe. Were there any questions from the homework? Homework is 46 to 49. Nothing? Okay. Changing temperature then. This is on page 50, 50. So there are, if you recall, 3 stresses. What are the 3 things that can be stresses? Tell your partner, what are the 3 things that can be stresses?
Gotta look back. Straight up for gone. Oh yeah. Oh yeah. I think so.
Okay, are we ready? What is one of the things that is a stress, Coco? Pressure, yeah, pressure / volume. That's the one you did over the weekend. What's another thing that is a stress, Taran? Concentration. And the third thing, Isabella's not here. Eric. Pressure, sorry? Temperature, yes. So we did the other 2 last week, and today we are going to do temperature. And of course, when we say these are all changes in a change in pressure, a change in concentration, or a change in temperature. So if we look at this reaction here on page 50, is the forward reaction endothermic or exothermic? Page 50. Exothermic. Is the reverse reaction, so this is our forward, is our reverse reaction for endo or exo? Just here? Yeah. Reverse is endo. Which reaction has a higher activation energy? Ooh, that's something to think about. Well, what I'd like you to do is I would like you to graph the reaction and then look at it from the forward direction, look at it from the reverse direction, and then decide who has the higher activation energy. So who has the higher activation energy? Reverse, because our forward, that is the activation energy forward. And our reverse is from the products to the peak. That's our reverse. So no matter what the circumstances, which reaction will always have the higher activation energy? The endothermic. What happens to the forward rate when the temperature is increased? And why? Tell your partner. What happens to the forward rate and why? You can look on my ad.
But it's only our first quiz. It still says 55%.
What? No, it should be updated now.
Oh. Because I checked yesterday, it still said 50.
Yeah, that's because I updated it like when I got to school this morning, so like half an hour ago.
Uh-huh.
I print them out for my grade 9s because they can't figure out how to get onto my ed, let alone like check their progress report, a lot of them. But for you guys, I trust that you can do that.
We are highly intelligent.
Because you are highly intelligent, basically almost adults. Are we ready for me to pick a card, or do we need a little more time? When we increase the temperature, what happens to the forward rate, Kiona? It increases. Why does it increase? Sambed, what is one reason why the forward rate increases when temperature is increased? The molecules move faster, therefore what? Therefore there's more collisions, yes. Is there anything else to that answer?
Yes.
Yes. What else is there to that answer?
Energy, more percentage.
Yeah, a higher percent of collisions have sufficient energy. What happens to the rate of the reverse reaction? Everybody should be able to tell me this.
It should go both ways. So.
Have a chat with your neighbor. What happens to the reverse rate when the temperature is increased?
Unless we are.
Yes.
Yeah.
What happens in that moment when we increase temperature? Oh, I cannot have. So sorry. You're like, what is happening here? No, you're good. You're good. Yeah. No, sometimes I just suck at adding.
Okay.
Yeah. Thanks for catching that. Perfect.
Oh, really? No, but that was the beginning.
How I don't remember all
Okay, everyone, we're going to vote on this. Does it increase, decrease, or stay the same?
the
It increases. Yes. Okay. Why?
same reason.
Same reason. Same reason the forward rate increases. Now the question becomes, which rate is increased more? So here we have our kinetic energy diagram, right? It says energy, but it should say kinetic energy. And out of these two diagrams, which one represents the endo and which one represents the exothermic reactions given their activation energies? Which one is the endothermic and which is the exothermic? They are both for this reaction here.
So it's 2x, so it's 1. Wait, other way around.
Do you guys agree with Owen?
Endo is 1x, so it's 2.
Endo is 1, exo is 2.
Wait, what do you 1 and 2? Wait,
I will say this one in next. This is the reverse, which is wait, I think it's. Oh, what do you mean? I don't think so. Reverse, yeah. And you don't know. Yeah, higher. So this one is. And so less
What do we think? Is the first one the endo or the exothermic reaction?
I think it's the endothermic because it requires less energy.
The first one, the activation energy is that much. The second one, the activation energy is that much.
What? I know, I didn't remember.
No, they're not the same, right? If you look at this one, this is here.
Oh, wait, no, yeah, that's yeah. Like that.
So who is the endo, who represents the endo and who represents the exo?
Exo is number 1.
Yeah, we have a bigger activation energy for the reverse reaction. And we have a smaller activation energy for the forward reaction. Does that make sense? So what that means is that the first one is endo. And the second one, and that is the reverse direction. The second one is exo, so that is the forward direction. And now we're going to look at 2 samples of molecules. We're going to look at the colder one. This is at our lower temp. You'll notice the peak is higher, the peak is further to the left, and it ends sooner. This is at a higher temperature. So if we look at, could you guys shade the area where we would have particles that can do successful collisions at the lower temperature? particles with successful collisions at the lower temperature. Do you remember how to do that?
Wait, what is particles in the dash in this thing?
With. That's a C. Does that ring bells?
Yeah.
That little blue shaded area there? Okay, that's those ones that are above the activation energy are able to react. Okay, those are the particles we can have successful collisions with. And I made my approximation. You remember when we did this and we made our approximation and said what percent of the curve is that or what fraction of the curve? I made a guess and I said that's about 1/25. Okay, so that's about 4%. All right. Where would we shade for the higher temperature? What would we do for the higher temperature? Where would we go? Everything under the red curve. Okay, and that looks to be about how much? About how much percent? About 50%. So if we say, how many times more effective collisions do we get? 50 divided by 4 is 12.5 times. That's how many times more effective collisions at the higher temperature?
12.
Yep. So that's quite a lot. Let's get more than 10 times the effective collisions. Okay, let's look at our exothermic reaction, the forward direction. Why you not move for me? There we go. Okay, let us shade our low temperature effective collisions. That is the area under which curve? Under the blue curve. And where do we start? At the line, at the activation energy. Anything over that has more than the activation energy. So those are our low temperature effective collisions. Our high temperature effective collisions where do we shade? Underneath the red one. Okay. So we've gone from the blue one. The blue one had approximately 25%. of the area under the curve is effective. And the red one looks to be about 2/3 effective. So we say, how many times did this go up? Well, 67 divided by 25 is 2.7 times. In which situation did we have the bigger effect? Did we have the bigger effect for the endothermic reaction or the exothermic reaction? Endothermic. All of this, you're not going to need to explain this, okay? But again, it's one of those things where if you think through it and you can understand it, then hopefully, you can remember it better. All you really need to know is that an increase or decrease in temperature affects the endothermic reaction rate more, okay? The endothermic rate is affected more. So that's what we have on our next page. Changing the temperature affects the rate of the endothermic rate more. Always. Because if you were to draw that graph, anytime, it's going to make more of a difference when you have a bigger activation energy. Okay, because it puts it down into the larger section of the curve. Yeah. After increasing the temperature, which rate is faster, forward or reverse, and why? And remember, the forward is exo, and the reverse is endo. And when we increase the temperature, what happened to both our rates? Both our rates increased. Which one increased more? Forward or reverse? Reverse. So we're going to end up with both rates faster, but the reverse rate is more faster. Okay, I know that's not good grammar, but whatever. The reverse rate is faster because an increase in temperature increases the endothermic rate more. And if that's the case, if we're looking at those two arrows, what is being made faster? Product, oh, sorry, yes. Okay, so both rates get faster because the particles are colliding more, yes? The reverse rate is endothermic, and endothermic reactions are affected more by a change in temperature. Because if you look at the graph, when you have the exothermic rate always has, the exothermic reaction always has the endothermic reaction always has a larger activation energy. Yeah, so our endothermic reaction has larger activation energy of the two. So when you move your graph to the higher temperature or to the lower temperature, you are moving a larger portion of molecules into or out of the active zone, the ones that can react. So you can see we go from the blue amount here, right, to having all this much more, right? Whereas down here, we go from having the blue amount here to having this much more, which is still more, but it's just not percentage-wise as much more. Like it's only 2.5 times more, whereas the other one is like 12 times more. Did that make sense? Yeah. You don't need to be able to explain this. Okay, you just need to know that the endothermic rate is affected more. Okay? But it was a very good question, and I like that. Okay. What is being made faster? Products or reactants? Reactants. Since the reverse rate is faster. And if the reverse rate is faster and we're making reactants faster, the system is shifting which direction, left or right? Left. And now we can make a rate diagram. What goes on the y-axis in a rate diagram? Rate. Shocking. Okay. And on the x-axis? Time. And of course, we start out with our forward and our reverse rates being equal. And remember, should there be a big gap between them, or should they basically touch? They should basically touch. Now, at this time right here, we increase the temperature. Remind me, what happened to the forward rate? It increased. What happened to our reverse rate? It increased. So we're going to have the forward rate go up. The reverse rate should go up more, less, or the same amount. More, because remember the reverse rate is the endo. It's affected more by a temperature change. So the reverse rate goes up more. Tell your partner what that graph will do now. Yes, I heard a bunch of people. I saw the hands. What should it do, everyone? Yes, they're going to come together. Okay, this one is going to start here, and it's going to go up, steep, shallow, flat. And then this one's going to go down, steep, shallow, flat. So that is our rate diagram. Concentration diagram. We have, what chemicals do we have? We have N2, H2, and NH3. Concentration, time, And right here is where we increase the temperature. And remember, this was our energy here. So our forward rate is faster than our reverse rate. Tell your partner what will happen to each of the concentrations. First of all, which concentrations spike?
Which one's like N2 and H2?
The N2 and H2?
I mean, all of them spike.
All of them spike. So we have some choices now. We got N2 and H2. Any other choices anyone wants to put into the pile before we vote? Okay, and before we think about that, I want you guys to imagine that you are all molecules. Yes? You are all molecules. And I've told you, wander slowly about the room. The room has been emptied of all furniture, so you're not going to like bash into things, okay? Move slowly around the room. And then all of a sudden I say, move faster, start running, go, go, go. What happened to the number of students in the room? It stayed the same. So the concentration of which one will spike? None of them. Because we've not done anything to the concentrations. We've not added any particles. We've not shrunk the volume. And remember, concentration is number of particles over the volume. We did not change the number of particles. We did not change the volume. So there's no immediate change to concentrations.
So we just leave it like that.
So there is no spike in any of the concentrations. Is there a shift?
There could be. Because we didn't change anything.
Will we see a curve on any of these, or all of them, or whatever? Have a chat with your neighbors about that.
Yeah, because I not.
Are we at equilibrium? No. So is there a shift? Yes. How can there not be a shift if the reverse rate is faster than the forward rate?
But how does it go back to where it started?
It doesn't, because temperature changes equilibrium in a different way. Okay? When you change concentration or when you change pressure, the system is shifting to keep the concentration of the ratio of the concentration of products to the concentration of reactants the same. Okay, so the system is like, the ratio is out of whack. We need to get back to the original ratio. But when you change the temperature, you change the ratio. Okay, and that is because the reverse rate is faster and the forward rate is slower. So there is no way that you cannot be making N2. Yeah. And making H2. And using up NH3.
So is that correct?
So this is correct. Yes, because we are making N2, we are making H2, and we are using up NH3, and they are in a 1 to 3 to 2 ratio. And so this ratio of products to reactants changes when temperature changes. Yes. Because the stress was, the spike signifies the stress, yes? The stress was temperature. The spike is here. So it only changes the rates. It does not change the concentrations. The stress was, the stress doesn't show up in the concentrations because we didn't change a concentration. Uh-huh. We aren't doing that. The system is doing that. So it's not a stress, it's a shift. Yeah? So we did nothing to the concentrations. We did something to the temperature, which only changes the rates. Yes. Yes. Stresses are what we do to the system. The shifts are what the system does in response. Yes. I could have written that better so it didn't like overlap all of this. There we go. Okay, here. Oh, there we are. Okay. So stress is what we do, shift is what the system does. When the stress is temperature, there is no spike in the concentrations. Oakley dokley? Okay.
Are we eventually gonna add all the stresses together?
No.
Oh, no.
We will do them like sequentially, but not all at once, right? It might be like you see a diagram and you'll be like, it does this and it does this and it does this. And I'm like, what changes were made here, here, and here? Okay, that ratio does not change when the stress is concentration or pressure. The system shifts to make the ratio go back to where it was. All right. Le Chatelier's perspective. First of all, it's been a whole weekend. Define Le Chatelier's principle.
Can I go back?
Well, why don't you think about it first? Le Chatelier said, I'm going to start you with the first word, when. System. Oh, great. System. That'll get you started. When a system. Okay, so we're just doing a noun right now. There's no verbs yet. Okay, we're just doing a descriptive phrase. When a system, what is that system like? At equilibrium. Okay, so that's our first phrase. When a system at equilibrium, and now we can add a verb. What do we do to that system? Is stressed. So we got a system at equilibrium when it is stressed, comma. We need another noun. Could be the same noun. System.
System will shift.
Will shift.
Shift back to something. So the system will shift back into equilibrium, or
In order to do what?
release the stress.
Relieve the stress or minimize the stress. Okay, so there's really 4 parts to that. When a system at equilibrium, what's happening to it? It is stressed, then the system will shift. Why? In order to minimize the stress. So from Le Chatelier's perspective, if we look at our forward reaction, does it absorb heat or does it release heat? The forward reaction releases heat, and the reverse reaction absorbs heat. If we decrease the temperature, remember that's a stress. Because that's what we did. What has happened to the amount of heat in the system? It has decreased, because what we've done is we've maybe placed the system in an ice bath, and the motion of the molecules, they're bashing into the sides of the container, and that motion is moving out into the molecules in the surroundings. Okay, so the amount of heat in the system has decreased. According to Le Chatelier, the system will shift in the direction that, do we want to absorb heat or release heat? Do we want to bring the temperature back down or do we want to bring the temperature back up? We want to bring it back up. In order to do that, we want to shift in the direction that will absorb heat or release heat. If you absorb heat, remember it gets turned into potential energy. Release heat to bring the temperature back up. And if we're shifting in the direction that releases heat, the system is shifting to the right. Yes? So here's our shift. We are releasing these kilojoules here. Remember, this right here is kinetic energy. So if we release more heat, that means we are producing kinetic energy. Okay, so release heat means turn potential energy into kinetic energy. And remember, kinetic energy can be measured as temperature. Now, if you like the pulley system, you can treat the heat term as a product. You can say, here's my heat term. If I decrease that, and I put my pulley here, and I have my pulley here, which way is the string going to be moving on the top? If this part is moving down, this is going to be moving to the right. Yes, so it is shifting to the right. If you like the arrow method, head to tail arrows.
Didn't we just say on the other page it's shifting back though?
Hold on. On the other page, we increased the temperature.
Oh.
Now we are decreasing the temperature. Okay, if you like the arrow method, you can say, okay, this one, whoa, I need to give myself room there because I don't have the temperature. N2 plus 3H2 goes to 2NH3 plus kilojoules.
Is this question solvable?
Yes, that's your overall reaction. Does that help?
Oh, okay.
Yeah. Okay. If temperature goes down, that means the kinetic energy goes down. Yes? Which means that essentially this is going down, right? And then we draw our arrow going across, head to tail. We are now going to be producing kinetic energy to bring the temperature back up. Yeah? There is, if you're explaining it, it is actually okay just to say decreasing temperature favors the what kind of thermic reaction? Decreasing temperature favors endo or exo? Exo. Since it releases heat to bring the temperature back up. If you don't like this, since it releases heat, if that's confusing to you, you could say it turns potential energy into kinetic energy. You could say that instead, right? So this part here could take the place of this part here if you wanted, okay? Increasing temperature always favors the endothermic reaction since it absorbs heat, which will bring the temperature back down. Because remember, when we absorb heat, we take kinetic energy and we turn it into potential energy. Okay. Rate diagram, concentration diagram. We are going to do this when our stress is a decrease in temperature. Do you guys think you can do it on your own? Or do you want me to walk you through it? You want to try it on your own? Try it on your own.
Oh my gosh, so much better.
So the reaction is actually our reaction so when we happen here, so
Why? It's for the sun. Running events. The body on.
yeah, and then
Trust me, I know. Yeah. What? It's just.
it's different.
Well, you have to like walking through it before the game.
You need to, I know. You need to.
I'm gonna go for it. Like, this is- If we produce more. Because. Concentration factor on time you go. Like, yeah. But that's fine. Really big.
I don't have to drive at lunch. We're gonna try it online. Not very good. But
Oh, is there a race boy? We do that.
hold on.
I didn't know we gotta see.
Hold on.
Yes, I literally forgot though.
Oh, just
But we're testing.
comes
that.
up paper with it.
We're testing it up because I don't have to go driving that much.
Yeah.
What? I have rice crackers that got out.
No, I think. Yeah. But don't you think they would have worn? Really?
Wait, no, I have some fun.
No.
But today's a freaking rainy ass day. Who's gonna bring?
No, but like they might just like have them.
No.
No, okay, no worries.
Yeah, we don't want to use Sharpie.
Thanks for trying.
That was a bad idea.
Yeah, let's just
I
run.
think I need some windows now. Okay, let's do this really quick. Give it your old good college try. It should look like this. I'm not going to do my axes because I'm lazy. There's our forward. There's our reverse. Maybe I will do my axes. Rate, time. Reverse, we decrease the temperature. Both rates go down, but the reverse rate goes down more. So the forward rate should go down, the reverse rate should go down more.
The reverse rate should go more.
Yes, because it is endothermic, so it is affected more. Endo is affected more. So both rates decrease.
But is it the?
Both rates decrease. Endo rate decreases more.
But isn't the forward rate exothermic this time?
Yes.
So shouldn't the?
Endo rate decreases more.
Shouldn't the?
Reverse is endo.
So shouldn't it be less?
So the reverse rate ends up being less than the forward rate. Yes.
Oh, you were. Oh, yeah.
Both rates decrease, endo rate decreases more. So the reverse
decreases what?
The reverse rate decreases more.
I'm sorry.
If we look back at our previous diagram, our reverse rate went up more, yes? Because the endo is affected more. The endo is still affected more. Both rates go down, endo goes down more. Yes, endo is always affected more. Does that make sense? Okay, cool. That's why we do these diagrams, to clear up any misconceptions like that, right? Then we have a concentration. N2, H2, NH3. And our forward rate was smaller than, or sorry, our reverse rate was smaller than our forward rate. So we should be making NH3 and N2 plus 3H2 to NH3 plus kilojoules. So our N2 is going to go down because it's being used up faster than is being produced.
Hello, I'm
Hi.
not safe. Can you just need to get to the
Oh, it should be unlocked.
Yeah, yeah.
Oh, thank you. Yeah. Okay, so we have X. H2 is also going to go down. 1, 2, 3. 1, 2, 3. There we go. 3X. And NH3 is going to go up. I'm going to make a different color just so I can see it. 2X. Yes. Doesn't matter, right? Because if you have it at different just amounts, it does, yeah. Mine just happened to overlap. Yeah, no big deal. Yeah, cool. Are we good? Okay, cool. We have just enough time to go through the explanations and then send you home with your homework, okay? So let's do it. Okay. How to explain in terms of Le Chatelier and in terms of rate. So Le Chatelier if our temperature is decreased, the temperature was decreased. In this case, therefore, the temperature is going, or sorry, the system is going to shift to the
heat,
it's going to shift towards the heat term, yes.
or just for this.
So yeah, this one just does this example. You would use the same framework for other ones though, okay? It shifts right in order to release. Heat to bring the temperature back
To its original.
up. Now, in terms of rates, a decrease in temperature does what to both rates? It decreases both rates, but a change in temperature affects the rate of the which reaction? Endothermic. Endothermic reaction more. So the rate of the, so what I would do at this point is, because I have trouble getting that through my head, so I'd be like, okay, so here's my endo. Endo is going forward. No, endo is going backwards. So let's assume that was our original state. And then when we decrease temperature, this is exo, this is endo. My endo decreases more. So what that does is it makes the forward exo rate faster than the reverse endo rate. And honestly, I would have trouble doing that without literally saying, okay, here's my original state. And then when I decrease my temperature, I end up with that. So don't be shy about drawing the arrows.
On the quiz, draw as much arrows as you
Draw as many arrows as you need to, okay? If you don't need to, that's great. I mean, I could probably do it without them, but I don't know.
Oh, what's the cutest? Okay.
Yes. We have a quiz. Okay, I would love to have a quiz on Thursday, but apparently everybody has like 3 tests on Thursday. So I'm going to do it on Monday. All right, so you will have time to practice these lots. Although we're going to be moving on to the next thing tomorrow. Yeah? Yeah. So reactants and products are being made faster than, who's being made faster? Hold on. Who's being made faster, reactants or products? Products. And I would draw the R and the P there. Products are being made faster than the reactants. Therefore, the system is shifting right. Okay, here's another example. We have our endo and our exo. If our temperature is increased, which way does it shift? Yep, it shifts right in order to do what with heat? Absorb, to bring the temperature back down. In terms of rate, an increase in temperature does what to both rates? It increases both forward and reverse rates. So here's our original. And this is our endo, and this is our exo. When I increase the temperature, what should happen? No, the endo increases more. Endo always changes more. Endo always changes more. Okay, I'm going to not do that, but endo always more. A change in temperature affects the endo thermic rate more. Therefore, the endo, which is the forward rate, is faster than the rate of the exo reverse reaction, which means that products are being made faster than reactants, which means the system is shifting right.
Wait. In this case, both of them are shifting right.
Yeah, because they were the opposite direction and the opposite temperature change. Shh. We got one last thing to do. Shh. Remember our tubes? Remember brown and colorless gas? When we heated the tube, the solution became darker brown. So when we increase the temperature, which direction did it shift? The system shifted right. And if we increase the temperature and it shifted right, was that because it wanted to release heat or because it wanted to absorb heat? We increase the temperature. We increase the temperature. What does the system want to do? It wants to bring the temperature back down. And if it wants to bring the temperature back down, which way does it have to shift? It has to shift to absorb heat to bring the temperature back down. And if it is shifting right and it is absorbing heat, where is the heat term? Okay, we're shifting right, we're absorbing. We're shifting right, we're absorbing heat. Where is the heat term?
Yeah.
If we're absorbing heat, heat has to go in. Yeah? So the heat has to be in the reactants, which means the forward reaction is endothermic. 2.2D is for homework.
Oh my. I don't understand it.
Thank you. If anyone still has their test, make sure you return it before you leave. Otherwise, you get a 0.
It just got so much memorization. But if you like memorize enough of it, you can probably get like 100% no problem. But the thing is, do you really want to memorize all
All the chemistry? If you understand it, you don't have to know it. On the other hand, a lot of people in chemistry 12 still have to memorize it. It will come with time. See you later.
Thank you. Bye.
Me and Joe last started studying for is it possible for us to get worksheets from you? So we can look at two topics that we have covered.
Yes.
So if we just come to you and take the quizzes for them. If you want, we can return them back.
Sorry?
Can I see my test?
Yes.
Isabella, right?
Okay.
Sorry,
I'm like under all the thing and I'm like, I think that's Isabella. I like it with the shirt and the hair though. It's very
Everybody, like, you have a blue shirt. Like, you have to do like,
you have to do the go all the way. Yep, there you go.
thank you so much.
Yeah, just return it when you're done looking. Let me know if there's any questions. Gianna, do I have your test? Oh, you want it back? Yes. Thank you very much. You can see it in class. Because
I can't wait until class.
I got stuff to do for my grade 9s right now. Yeah.
No, I didn't see my test. I just saw my mark.
Did you not see your mark?
It's just low.
He failed, right?
No, I didn't.
He failed.
Totally failed.
We all failed. I also failed.
Did something go wrong with the Scantron?
I don't know what was wrong with my answer key. There were just things wrong with the answer key. So these are correct and that one was.
Okay.
Yeah.
Okay.
Anyway, so I changed the Scantron grade there.
Okay.
Yeah.
Thank you so much.
Thank you. You too.